All right, let's jump right in. We're talking about a huge piece of news from IBM today, something that could seriously change the game for practical, powerful quantum computers. They've found a shortcut, and it is a big one. So, let's start with this number, 10x. That's how much faster IBM's new error correction algorithm ran. And here's the kicker. It did it on standard, off-the-shelf hardware. This isn't just some small tweak. This is a massive leap forward on one of the toughest problems in all of quantum computing. Okay, so here's our game plan for this explainer. First, we'll look at the shortcut itself. Then we'll get into the massive problem it helps solve. We'll talk about the surprising role classical computers are playing, weigh the different reactions to this news, and then we'll connect it all back to what this means for your data security. Now, this isn't just another routine update from a lab. IBM is calling this a major breakthrough, one that's put them a full year ahead of their own very ambitious roadmap to build a large-scale quantum computer by 2029. So, to really get why this is such a big deal, you have to understand the biggest headache in quantum computing. The building blocks, the qubits, they're incredibly fragile. Think of them as being super sensitive to the slightest disturbance, which causes a ton of errors in their calculations. Honestly, building a useful quantum computer is pretty much all about taming these errors. And the tool for that is something called quantum error correction, or QEC. The best way to think about it is like a super advanced spell checker for the quantum world. It has to find and fix mistakes on the fly, all without actually looking at the qubits and destroying their delicate quantum state. You can't have a real quantum computer without it. It's just that simple. And this is where you can really see the before and after. IBM's old way of doing this spell checking, a decoder called BP plus OSC, well, you don't need to remember the name. You just need to know it had two massive problems. It wasn't very accurate, which made the whole process inefficient. And even worse, it was just too slow. It would have actually become a bottleneck for the whole system. But the new method, Relay BP, solves both. It's way more accurate, and critically, it's fast enough to keep up. But you want to know the wildest part of this whole story? This super advanced quantum algorithm wasn't running on some futuristic, custom-made chip. Nope, it was running on a standard AMD FPGA. That's a type of reprogrammable chip that you can basically just go out and buy. The hero in this quantum story was a classical computer part. And this just perfectly shows you what the future of computing is going to look like. It's a partnership. Classical computers are going to be the essential co-pilots for quantum systems, managing all the critical background tasks, just like this error correction process. Using standard parts like this lowers costs, means we're not so reliant on one-off custom pieces, and makes the whole setup look a lot more like the data centers we already know. Of course, with any huge announcement like this, the debate begins immediately. So what is this? Is it a deluge, a flood of progress that changes everything? Or is it maybe just another small drip in a very, very big bucket of challenges we still have to figure out? Which brings us right to the main question, right? How big of a deal is this really? And, well, depending on who you ask, you get some very different answers.
So on one hand, you have the optimists. They're saying, look, this is a major step forward. Getting a year ahead of schedule on a plan this ambitious is no small thing. It shows that one of the absolute hardest engineering problems, handling errors, is solvable.
But then you've got the skeptics, and they're pumping the brakes a bit, saying, hold on. With so many companies and researchers working on this stuff, one improvement, even a good one, is really just an incremental step. It doesn't magically change the entire landscape overnight. The core of the skeptical view really comes down to this. This is a win for the software and the control systems, not for the fundamental physics of the qubits themselves. And the biggest hurdles, those are still in the hardware. They argue that getting a useful computer by 2029 still depends way more on making the qubits themselves better and more stable. And sure, making things cheaper is nice, but let's be real. The first customers for these machines are not going to be worried about the price tag. Okay, so let's pull this out of the lab and talk about the real world. Because whether you think this is a drip or a deluge, this progress has a direct and pretty urgent implication for every single one of us, the security of our entire digital lives. See, here's the reason governments and corporations are pouring billions and billions of dollars into quantum research. It isn't just for science. It's because a quantum computer that's powerful enough will be able to shatter the encryption that protects, well, everything. Your banking, your private messages, top secret government data, all of it. And the sheer scale of this problem is just mind-boggling. We are talking about over 20 billion devices out there, phones, servers, cars, you name it.
that all rely on encryption that is on the verge of becoming obsolete, and every single one of them has to be updated.
So this has put us in a very real race against a quantum clock. Right now, our encryption is vulnerable. There are new standards being rolled out, but the final deadline is the day a quantum computer powerful enough to break the old stuff arrives. And every breakthrough, like this one from IBM, makes that clock tick just a little bit faster.
And this is how it all connects. Why does this specific breakthrough make that security clock speed up? Because by using common, off-the-shelf chips, it makes building these powerful systems cheaper and less complex. It makes the whole process more reproducible, which could put this incredible power into more hands and potentially sooner than anyone expected.
The whole pace of this field has just changed. What used to be a distant, almost theoretical threat you'd read about in scientific papers, it's now become a steady drumbeat of new announcements week after week. Those sparse signals of what's coming are now dense, and they are all pointing in the exact same direction. And that leaves us with one final and pretty urgent question. As every single one of these breakthroughs pulls that deadline closer and closer, you have to ask yourself, are we moving fast enough to update our defenses? Or is time about to run out on securing our digital world?